the first time in Texas, all 254 counties are under a winter storm warning. The temperature in Dallas already colder than in Anchorage, Alaska.
In February 2021, Texas had a winter storm that hit the state hard.
We know about 4 million customers also without power, more than 3 million of which across the Lone Star State.
Here in the U.S., winters are warming faster than any other season. But then why are some winter storms getting even more intense? Could climate change be making some of our winter storms worse? I'm your host, Lar Hesse-Fisher of the MIT Environmental Solutions Initiative, and this is Today I Learned Climate. Today, my guest is going to help us understand the connection between climate change and extreme winter weather.
My name is Jennifer Francis. I'm a senior scientist at the Woodwell Climate Research Center in Falmouth, Massachusetts. And I'm an atmospheric scientist, so I've been mainly focused on the atmosphere in the Arctic.
Dr. Francis told us that to understand what's happening with winters in the U.S., we need to first understand what's happening in the Arctic. The Arctic is the northernmost part of our planet, a region of land, sea ice, and ocean that surrounds the North Pole at the top of North America, Scandinavia, and Russia. And it's ground zero for global warming.
The Arctic is warming about 4 times faster than the globe as a whole, and that is having all kinds of impacts on the ice up there.
Especially sea ice. The Arctic is about 60% ocean, much of which is frozen over.
It actually forms from seawater, so it freezes up during the fall and winter, it gets thicker and thicker, and then when that ice starts to melt, it exposes more of the underlying ocean. And so instead of having this reflective white surface that sends most of the sun's energy that hits it right back to outer space, when we have less of that ice, that sun's energy instead goes into the ocean and warms it up, which melts even more ice. And so that exposes even more of the dark surface. And so we get this vicious cycle. All that extra energy that's going into the Arctic Ocean, where that ice used to be, is the main contributor to the fact that the Arctic is warming so much faster. It's been estimated that global warming is 25% to 40% larger than it would be if we didn't have these Arctic bright surfaces disappearing.
Wow. Hang on a second. Let's repeat that.
It's been estimated that global warming is 25% to 40% larger than it would be if we didn't have these Arctic bright surfaces disappearing.
That is an incredible impact. This warming has big consequences in the Arctic, from roads sinking because they were built on permafrost, to polar bears drowning, to lost ways of life like traditional hunting on the sea ice. But the Arctic warming can also make the weather further south kind of wacky. And to understand why, we need to quickly learn about the jet stream. There are 4 main jet streams on Earth, and we're going to talk about the northernmost one. It flows over North America and Eurasia, a little south of the Arctic.
The jet stream is this fast-moving river of wind high over our heads. The winds blow from west to east. The reason it's called a jet stream is because it exists up where jets tend to fly.
Yeah, the jet stream can blow at more than 100 miles an hour. So pilots actually tend to fly in the jet stream to get a little boost. That's why your flight going from, say, San Francisco to Boston will be shorter than the return flight east to west. These rapid winds form because the cold air of the Arctic is meeting the warm air closer to the equator.
Warm air takes up more space. So if you can think about a layer of the atmosphere that extends from, say, the middle of the United States up to the Arctic, it's going to be a taller, thicker layer in the south. And then as you go north, where it gets colder, that layer shrinks because air shrinks as it gets colder. So if you can imagine sitting up on top of this layer looking northward, it would look like you're looking down a hill, which in fact you would be. And the air on top of that layer wants to flow down that hill just like water wants to flow down the side of a mountain.
And as the air is falling downhill, north, it's also being pulled to the east by the rotation of the planet. This creates the jet stream. Now, sometimes the jet stream curves north and south. It might, say, dip from Idaho down south to Kansas, and then maybe go back up north around Maine. But lately, the jet stream has been changing.
Because the Arctic is warming so much faster, we're seeing that north-south temperature difference get smaller. And because it's smaller now, a lot smaller than it used to be, we're seeing the winds of the jet stream actually get weaker.
The hill is less steep, so the air doesn't flow down it as quickly.
And when the jet stream winds get weaker, it tends to get deflected more to the north and south. That allows that cold air to penetrate much farther south. And those big waves in the jet stream also tend to move much more slowly from west to east. So the result is, sort of the bottom line of all this is that the weather patterns that we experience feel like they're getting stuck in place.
And that's how the ice melting in the Arctic can make cold spells last much longer and go much further south down here in the US. Now, we've gotten this far without talking about something you've probably heard about in the news, the polar vortex.
I think the polar vortex has gained so much traction because it sounds scary and horrible. You know, you think of a vortex being like something that's going to suck people in and they're going to disappear forever.
But the polar vortex is a normal, natural thing. Just like the jet stream, it's a river of fast-moving air.
But it's much higher in the atmosphere than the jet stream is. And it's much farther north. It sits up over the North Pole.
Every couple of years or so, the polar vortex stretches out or even splits into 2 or 3 separate swirls. This can nudge Arctic air into the jet stream and push it further south.
And this is actually exactly what happened during the Texas cold spell of February 2021. We had one of these pieces of the polar vortex that drifted down over the middle of North America.
That natural event was paired with a slower, weaker jet stream.
And it made that cold spell more severe, longer lasting, and it made it dip even farther south than a normal cold spell would. Dallas was minus 2 degrees Fahrenheit.
In that 2021 storm, millions of homes lost power because the state's energy infrastructure couldn't keep up with the cold, just when people needed that power the most to keep warm. Okay, let's switch gears for a moment and talk about that other staple of winter weather, snow. A warmer planet means less snow, right?
In places where snow is kind of marginal, like right along the east coast of New England, we're going to see more rain because it's just warming that much more.
Right. This is straightforward. In some places, even a few degrees can make the difference between snow and rain.
But the opposing factor is that as the oceans warm and as the atmosphere warms, evaporation from the oceans and the land increases. And so that puts more water vapor into the atmosphere. So when you do get a snowstorm, there's more water for the storm to work with. And so we're seeing the possibility anyway of getting heavier dumps of snow in places where it's cold enough.
So in places that have very cold winters, like the upper Midwest or much of Canada and far northern Eurasia, they might see more snow as the climate warms. And even places with milder winters are seeing larger individual snowstorms, even as they get less snow on average over the year. So, even though on average winters are getting milder, a warmer planet can cause storms that are longer, colder, and snowier. And this is in keeping with other impacts of climate change. Things are a little warmer, yes, but what we notice most is that it's more extreme.
It was an incredible winter back in 2021 with that amazing cold spell. It wasn't just in the center of North America. At the same time, they were having an extremely devastating cold spell in Eurasia. These extreme events never happen in isolation. And that's because when the jet stream gets into one of these very wavy patterns, it's not just in one place. It tends to be around the whole northern hemisphere.
That's our show for today. As always, you can check out our show notes to dig deeper into what we covered in the episode. And this episode's educator guide explores the jet stream and polar vortex and allows students to get hands-on with the albedo effect. You can find both at tilclimate.mit.edu. TIL Climate is produced by the MIT Environmental Solutions Initiative at the Massachusetts Institute of Technology. David Lashansky is our editor and producer. Aaron Kroll is our associate producer and did our artwork. Natalie Jones was the scriptwriter for this episode. Michelle Harris is our fact checker. Sylvia Scharf is our climate education specialist. Adam Nakov is our student production assistant. The music is by Blue Dot Sessions, and I'm your host and producer, Lar Hesse-Fisher. Thank you to Dr. Jennifer Francis for speaking with us, and thank you for listening.